Good morning, everybody. We are glad and proud to present you work of research and pedagogy on the specific typology of suspended braided structural shells. This work has been performed for a full-scale public pavilion called Baya in collaboration with the Paris City Hall and the 19th District City Hall by the students and teachers of the School of Architecture of Paris-La Villette and of Engineering of Centrale-Supélec of Paris.
When you think about how a bird's nest works, reciprocal frame is the first idea that comes to mind. The structural typology forms a surface composed of inclined beams supporting each other. The end of each beam rests on the next beam that supports it, forming a circularly closed assembly since the last beam is finally placed on the first one. Each element mobilizing by bending the many other elements that intersect it. However, it leads us to a new structural typology as part of this larger group of reciprocal structure, braided objects on which is based the art of basketry.
There are many different braiding techniques. The ones we have used are croquet and layer. This analysis resulted in the selection of three materials for the project: buff wicker, split wicker, and rattan blades. Wicker is obtained from willow stems, which can reach up to 3 meters. They are harvested in winter from willow stems. There are 4 types of wicker. Wicker is row-dry when it is dried naturally by keeping the bundles upright. After drying, the bark can be removed from the stems. The wicker is then dried again. It will be left in water for 8 to 15 days before weaving in order to soften it. It is interesting to note that basketry examples can be found in nature, as for social lubricants, gaskets, or even weaver ants.
Basketry applications can also be found in primitive or vernacular habitat. Some examples are also to be mentioned in modern architecture. However, all of them, with few exceptions, have in common that braiding is only used as a filling element. It is not structural.
Our goal is to transpose the basket maker's skill to an architectural work. Our project, Baya, is a suspended pavilion, but our thinking is broader. It must be applicable to any loaded surface, such as shells, as well as simpler elements like beams. Our purpose is to study the constraint fields in the shell and to question the existence of an optimal braiding of the shell in relation with them. Our numerical simulation is conducted by dynamic relaxation, a method that allows us to solve static equilibrium problems by fictitious dynamic calculation. The braid is a set of strands braided in 2 different directions. In each direction, the strands are parallel to each other and pass alternately above and below the strands of the other direction. The specimen is subjected to forces that simulate the principal stress field in the shell. The study of the specimen teaches us the following principles. As expected, the yield ratio is a linear function of the tension. Local buckling is not an issue with regular densities. Global buckling depends mainly on compression. Friction forces rise with tension and fall with compression, which explains why instability failure appears with lower compression when tension is not high enough. High values of compression leads to knots, translation or rotation, even decompression. Changing the braiding angle has little effect if input forces are almost parallel to the strains with alpha close to 0, which validates the idea of braiding along the principal traces. As the results couldn't be compared with the bibliography, since we did not find any equivalent studies, it was necessary to verify them by similar experimental study.
By algorithm determines the principal stresses for any shell under a given load. Thanks to the optimal braiding laws, it is able to give the ideal braiding for the shell. Algorithm can be applied on any loaded surface, including basketry items, and we have chosen to illustrate its presentation on an isostatic beam on 2 supports loaded by a uniformly distributed force. The shell geometry and loading are the input. The surface is discretized into small rectangular isosceles triangles, each representing a finite element of it. Then we calculate efforts on the finite element edges by dynamic relaxation, and we deduce from it the principal stresses in the finite element. By using the laws defined previously, we eventually obtain the optimal braiding of the shell. After the study, we decided to braid the result in order to compare our Baya beam to a Pratt truss. For identical sizes, loads and safety factors, baya needs half the quantity of Pratt.
We also performed an experiment called photoelasticity. We compared the principal stress fields obtained from the Baya algorithm to the isoclines of a shell made out of a birefringent material.
We tested another method to control the effort obtained in the edges of the finite element by the Baya algorithm. We filled a suspended balloon with water because the pretension it induces gives the capacity of compression to the balloon's skin. We loaded it with a mass. A picture analysis algorithm recognizes marker points on the balloon and converts the grid deformation into strength thanks to Hooke's law. The results are very similar to the numerical prediction.
The Baya project, described below, is a colony of suspended pavilions whose skin, the very structure of the object, is a braid of long and fine elements. Among them, it appeared to us that the one of the Baya weaver was an object particularly close to our attention. The Baya weaver is a small bird which lives in Southeast Asia and builds suspended nests. The objective of this part of the study is to answer the following question. Does the Baya weaver follow, when it makes its nests, the laws of optimal weaving that we have defined? To answer this question, we have first carried out a survey by laser surface scanner and by photogrammetry of the nest, support of the MAP-MAC laboratory and the National Museum of Natural History. The results seem to betray the ghost of the temporary scaffolding used by Baya weaver to build its nests. To confirm this, we scanned the nest with X-rays thanks to the help of Dr. Bandeau and access to the interior of the nest walls. Several authors compare Baya weaver's nest to the shape of the drop of water at the time of its detachment. Others, like Newton, prefer the comparison with a suspended and weighted down stocking. Thus, we carried out a comparative form-finding study looking for the shape minimizing the energy involved on the two systems using the Baya algorithm. The proximity of both shapes to the nest is ruling in favor of Newton. Before braiding the final pavilion, we decided to build a half-scale prototype. The deformation of the prototype was critical, but fitted the algorithm prediction. The observation of the loaded surface guided us to reinforce the density of the compressed area in order to avoid surface buckling. The park of the Baie du Chapeau Rouge is in the 19th district of Paris. After various tests, comparing numerical and model studies, we opted, following the example of Baya weavers, for the realization of several pavilions.
We would like to conclude this presentation by thanking all the students who have taken part in and all our partners who have contributed to the success of this work.